Hey everyone, and welcome to The Explainer. I am absolutely thrilled to have you joining me today. We're going to do something pretty incredible. We are going to take the completely invisible mechanics of three-phase electrical power, which is literally the lifeblood of the modern world, and we're going to make them completely visible. We'll be breaking down some, well, admittedly pretty dense engineering concepts into clear, bite-sized steps. So if you're ready to truly understand the grid, you are absolutely in the right place. Let's dive right in.
So here's our roadmap for today. We're looking at 1. The birth of three-phase, 2. Inside synchronous generators, 3. Decoding phasors, 4. Three-phase circuit analysis, and 5. Measuring three-phase power.
All right, let's kick things off with part 1, the birth of three-phase. People love to argue about who actually invented modern AC power. But as our source text points out, the three-phase system was actually independently invented by Galileo Ferraris and Nikola Tesla. It was this massive parallel breakthrough by two genuinely brilliant minds. Ultimately, it was Tesla's specific design that ended up being licensed by Westinghouse here in the US, which kind of set the standard for the whole shebang.
Moving right along to part 2, inside synchronous generators.
Now take a look at this absolute unit. This is a real synchronous generator, specifically a stator and rotor setup from the Petroleum Corporation Supergrascandum day. I want you to notice that highlighted empty space in there. That's the air gap. And while it just looks like a tiny sliver of nothing, it is absolutely crucial. That is the exact space where the spinning magnetic field from the rotor cuts across the stator coils, inducing massive amounts of electrical current through magnetic flux. It's where the magic happens.
If we sort of abstract that massive physical machine, we get this precise, nicely color-coded three-phase winding arrangement. As that magnetic rotor spins, it induces an electromotive force. Engineers actually map this out using Fleming's right-hand rule, which links motion, magnetic field, and current direction. And because these three sets of windings are physically spaced exactly 120 degrees apart, they generate three distinct currents that are perfectly offset in time.
Okay, part 3, decoding phasors.
Enter the phasor. Now, what is that? It sounds like something out of a sci-fi movie, but it's really just a mathematical tool. It takes complex phase-shifted electrical quantities and maps them out geometrically. Why do we do this? So we can easily calculate their addition. In fact, in a perfectly balanced three-phase system, calculating the vector addition of these phasors results in exactly 0, which, by the way, is exactly why a neutral wire often carries absolutely no current.
Look at these messy, overlapping sine waves popping up at 60-degree intervals. Kind of a headache to process, right? But check this out. This exact waveform translates perfectly into that elegant three-pronged vector diagram right next to it. By mapping out the amplitude as the arrow's length and the phase shift as the angle, all that complex calculus suddenly becomes simple, readable geometry.
All right, quick pop quiz to test your geometric intuition. If I give you a reference voltage vector, let's call it V, pointing straight to the right, picture in your mind how you would sketch V1 if it leads V by an angle of alpha. Got it? Okay, now sketch V2 if it lags V by an angle of theta. The trick here is remembering that in standard phasor diagrams, counterclockwise rotation means it's leading in time, and clockwise means it's lagging. It's literally just mapping time onto a circle.
Which brings us to part 4, three-phase circuit analysis.
Let's ground all this abstract math, literally, in the real world. If you were to pop open a modern industrial junction box, you'd see a typical three-phase, four-wire system. We've got our three hot conductors, the phase lines. Phase 1 is usually brown, phase 2 is black, and phase 3 is gray. Then we have our single neutral conductor in light blue. That's our return path and reference point. And finally, the completely non-negotiable earth or ground wire, rocking those green and yellow stripes.
So how do engineers actually wire these up? Basically, they use one of two primary configurations to connect the loads or generators. You've got the star configuration, which is also called the Y configuration, and then you've got the delta configuration.
Let's break those down. In the star setup, all three phases meet right in the middle at a common neutral point. Because of this geometry, your line-to-line voltage is actually the vector sum of two phase voltages, meaning it's significantly higher than the phase voltage alone. On the flip side, the delta configuration forms a closed loop. Here, the line voltage and phase voltage are exactly the same, but the line currents split and end up being higher than the phase currents.
Now here's a real game changer for engineers. When evaluating a messy circuit that mixes both types, they can mathematically convert a star network of resistors directly into an equivalent delta network, or vice versa. For instance, a star configuration with 150, 180, and 60 ohm resistors converts precisely into a delta loop of 780, 312, and 260 ohms. This little trick allows engineers to dramatically simplify incredibly complex circuits on paper.
Okay, I've got another quick thought experiment for you straight from the source material. Imagine a perfectly balanced star-connected generator and a perfectly balanced star-connected load. If you run an ideal conductor from the central neutral point of the generator to the neutral point of the load, will any current actually flow through that connection? Well, if we use Kirchhoff's current law, we know the sum of the currents from three perfectly balanced phases dumping into that neutral node is exactly zero. So, theoretically, no current at all.
And finally, we've arrived at part 5, measuring three-phase power.
To really wrap our heads around the math of measurement, let's look at a beautiful, tangible piece of hardware. This right here is a vintage analog watt meter. Now, to measure power, which is watts, this instrument actually requires two entirely separate internal coils. One is completely dedicated to measuring voltage, and the other is strictly for measuring current.
Because it's got those two separate coils, wiring it up requires some pretty strict systematic steps. Step 1, you have to connect the current coil in series with your line, so the flow goes straight through it. Step 2, connect the voltage coil in parallel across the load. Step 3, the instrument mechanically combines these two magnetic fields, moves the needle, and boom, you've got the power reading for that specific phase.
But here's the beautiful part. Measuring a three-phase system doesn't actually require 3 meters. This perfectly illustrates the brilliantly simple 2-watt meter method. By connecting wattmeter 1 between phases A and C and wattmeter 2 between phases B and C, you capture the complete dynamics of the system. Because of Kirchhoff's voltage and current laws, the total instantaneous power mathematically reduces to simply P1 plus P2. It's just a highly elegant engineering solution.
And that is the whole shebang. We've taken the invisible and mapped it out. But before you go, I want to leave you with this to chew on. How is this exact 19th century mathematical architecture, we're talking spinning rotors, perfectly spaced 60-degree sine waves, and phasor geometry, currently working, right this very second, to charge the battery of the device you are using to watch this explainer? Next time you plug anything into a wall, I really hope you visualize that invisible, three-phase giant spinning quietly behind the scenes. Thank you so much for learning with me today, and keep exploring.